All right, let's get started. Welcome to this webinar on model validation with ModelSkill. My name is Jesper Sandvig Mariegaard. I'm head of the data model integration team in DHI, and I'm doing this presentation today together with Henrik.
Hi.
And maybe you'll also introduce yourself, Henrik.
Yeah, I'm a program manager at DHI, interested and responsible for open source, and this is an open source library, so I think that fits quite nice.
Yes. And the topic today is the library called ModelSkill, which is a Python library for comparing observations and model results. It used to be called something different, FMSkill. So if you've heard that, this has now been reborn as a ModelSkill to show that it supports a much wider range of different models. And our overall vision with this ModelSkill is that it should be, or could be, a modeler's companion during the different phases of a water modeling workflow. So that could be all the way from the setup phase, which is typically an exploratory phase, and where you would want some interactive workflow to quickly sort of get a rough idea about your model's performance. Then calibration, which is typically a more structured phase where you tweak and tune a couple of model parameters to get the best performance. And then finally, the validation and reporting, where you may compare to other models and so on. And when we talk about skill in ModelSkill, that is a quantitative measure with plots or numbers that somehow signifies the performance of the model. ModelSkill is basically performing two tasks. So matching of observations and model results, and then the analysis of the of the matched data. So when you're starting with ModelSkill, the first step is then to perform the matching. So you may have one or more model results. So here I've shown some flexible mesh results, but it could also be time series data from say a free flow model or from other models. That's not important here. Then you have some observations, because that's what the ModelSkill does. It compares observations and model results. And then the step here with the matching is then to match. If it's just time series, it's relatively simple. There may be a bit of interpolation in time. If it's a 2D model result, then there's also like an extraction from that 2D model result to get to the right spatial positions and temporal position. And then follows the analysis phase. But in some cases, you may already have your model results and observations compared, and then you're not forced to go through this workflow of first defining observations and then model results and so on. Then we have a method called from matched, where you can go directly to the analysis phase. So let's have a look at the analysis phase. After having matched your data, so they are in the same, say that they have been organized, then you have an object called a comparer, which can be used to do various plots and aggregated statistics and so on. One comparer corresponds to one observation, so that could be from one station, but can have multiple models. These comparers can also be collected in comparer collections. And we'll get back to these two main objects of ModelSkill in a minute, but I think it's useful actually now to see how it looks in action. So our first demo out of two will be in the hydrology area. So Henrik, maybe you would like to share your screen.
Yeah. So this is the GitHub repo that contains the examples that we're showing in this webinar. And I will show the hydrology example here. And if you want to try it out yourself later, I think it's quite easy to navigate here and then open in Google Colab. Which is a cloud-hosted notebook environment. So now we have the example here, but I need also the example data. So that's why I have this step here. And the first thing before we can do any ModelSkill assessment is to install the library, and then I will install another library that I also need for later. But ModelSkill is hosted on the same place where you can download almost all Python libraries, the PyPI. So it's a pip install ModelSkill. That's the first step.
Henrik, there's a question. Is it okay to take a question that's from Kuray?
Yeah.
So please, Kuray, then just unmute and ask your question.
Sorry, I didn't have any questions. It was a mistake.
Okay.
No worries.
Thank you so much.
But if you have questions, anybody, just raise your hand. So
yeah, so thank you, Kuray, for showing how you can raise your hand. You're welcome. Also, other participants, please do. Thank you.
Yeah. So this example, we have some time series data in a DFS0 file. So just inspecting this file here with our other library, Mike.io. You see we have some data from 2000 to 2010, and there are 3 different items in this data set: the observed discharge and the simulated discharge from one model simulation, and then a second model simulation. So these are already matched. So that's why we're using this method here from matched. So I imported ModelSkill as MS, and then now I'm using the from matched to create a so-called comparer object, and to make sure that things are correct here. Say the first item, that's the observation, and the second and third item, those are models. And I give this a friendly name. So now I have a comparer object of discharge at some named location with this amount of points, and we have 2 models. And a very common thing is just I want to inspect these time series in the time series plot. So then we can do like this in the comparer plot time series. And the default is actually matplotlib, but I think it's useful to have this interactive thing. So this is not quantitative, but it gives you a lot of insights. So I think this is a good step in doing model validation. Moving to something which is more quantitative, is this scatter plot, where we compare the observed discharge on the x-axis and the modeled discharge on the y-axis. So now we see creating this density plot. So where it's yellow, it means there's a lot of points, and then out here there are few points. And then we get the 1-1 fit, which would be like the optimal model, and then also a regression fit to these points. We also have these quantiles, so we can inspect the distribution. So that's the first model, and then we have the second model over here. We can also do this as an interactive plot. So as I said, the default is to use matplotlib, and most plots that we have for ModelSkill is made by matplotlib, but some, like the scatter and the time series, also support this plotly backend. I will also add this argument, the skill table, which you will see in a minute what it is. So now we have an interactive plot, which means I can click on and off points here. I can zoom into some specific region. And the skill table argument, it creates this quantitative metrics here. You see the number of points, the bias, root mean square error, and these quantitative metrics. So I think this is quite useful. I think the scatter plot with these things is like the bulk of model validation, but we sometimes want to do something else. We want to look at the statistics, like the distributions. So then we can use this kernel density estimation plot. So we can, maybe it's not perfect for things which are positive, but at least you can see that the distribution between these two model simulations and the observation is not identical. Another way of looking at those distributions is to look at the quantiles. So those are the same things as we saw in the scatter plot, but now we're only plotting the quantiles and both simulations in the same plots. So we can see that these could be two different model calibrations, or maybe one is a more complicated model and the other one is a coarse resolution model. I'm not sure exactly in this case. At least we can see that they follow like this similar pattern, but they are certainly not identical. To get some tables of these metrics, we could do it in the plot, but maybe we want to have like a more data frame like table. So we see model 1 and 2 at this observation. We get the bias, root mean square error, unbiased root mean square error, mean absolute error, and so on. So these are like the default metrics that we decide that this is good defaults, but as an hydrologist, you say no. We use some other metrics like the Klein-Gupta efficiency. We also use the Pearson correlation coefficient. So you can add these arguments to the skill method, and then you will get these metrics instead. And we can take a look at what metrics we have. So this is the documentation page for ModelSkill, specifically the metrics. And you see we have a number of metrics defined, and you can also get the definition here. So that's useful if you want to see exactly how they are defined. You can also look at the code to see how they are defined. So let's say that I'm tired of writing this in every line. I want to specify once and for all that these are the 3 metrics that I'm using in my project. So ModelSkill also supports some options. So I will set I want to use the KG, the Wilmot, and the Spearman rank correlation coefficient. These are now my new defaults. So when I call the skill method, these are the metrics I will get, but as obviously you can override this. So having a tabular output is nice, but you can also get plot this like with lines and bar plots. But now I'm going to demonstrate a bit powerful feature, because this is aggregated over this entire dataset, 10 years. But I can also give this by argument to the skill method. So now we have aggregated the skill over each year, and so this we can break in a line plot. So we see that the skill is varying a bit from year to year. Maybe something special about the 2007. We can dig deeper into that if we want. But another quite important part of natural systems is that they have a seasonal dynamics. So we want to compare the skill for each month. So here we have the KGE. So this is a bit special syntax. This one here, it says the frequency you can specify by day, hour, or year, anything that's supported by pandas. But if I would say I would specify by month, then it would calculate for each month during those 10 years, and that's not what I want. I want to aggregate for all Januaries and all Februaries. So now this is the skill in January across all the years, and we can see that the skill is perhaps a bit lower here during summertime, maybe low flow. I don't know. Maybe you should explain this syntax here. So we can calculate the skill, and then we selected a specific column similar to how you would do it in pandas, and then plot. Yeah, I think you get the point. So that was for one station, but usually we want to compare data for many locations. So I have this CSV file here with all the stations and the names and the locations, and also have some weighting factors. So I'm doing the same thing as I did before, using this from matched, but now in a loop. So I'm creating a lot of comparers, and then we have this comparer collection object that takes a list of comparers. So we see now I have the one I had before, and then a lot of different stations. I'm also creating these weights dictionaries, so I can do a weighted score, because I care mostly about this station, a bit about this station, and not so much about the rest. So this allows me to do a quantitative score, the Klein-Gupta efficiency, and then we can say specify the weights are equal. So that's without using this weighting factor. But I can also specify the weighting factor, and then you see it gets slightly different things. And this is the method that I would use if I would do auto calibration. So using this in an optimization loop. Yeah, so now we can see the score here for all of these stations, and compare the two different models. So that's nice if you know exactly where these stations are located, but if you're a spatial person like me who likes maps, you can also create a geodata frame. That's the GeoPandas library that you need in addition to ModelSkill. And that allows you to do something like this. And now we have a map here of the area, and these are all the locations, and we can see that in this region the model is not that good. Here is also not perfect, but here is really good. So I think this could be very useful in order to understand what is going wrong over here, at least if you're a hydrologist.
But I think the same would apply for coastal and ocean models, right? So,
obviously, yes. I mean, I cannot explain exactly why the model is wrong here because I'm not a hydrologist. So those are some plots which are built into ModelSkill and creating the geodata frame, but it's not like you're locked into the functionality that we provide in ModelSkill. Maybe you just want to use ModelSkill to calculate some metrics, and then you want to integrate it into a specific type of plot. So here I'm just doing the calculating the kg again, and then actually I don't like this sim1 and sim2. I want to replace those names of the model with something else. It's just for making a nice table, or actually for making a nice chart here. So this is using the Plotly Express. I calculated these things with ModelSkill, but I'm customizing it. So I think you get some plots like out of the box, but you can mix and match as you like. That's the point. Yeah, that's it for hydrology.
Very nice. Maybe should we ask if there are any questions at this point to Henrik and the hydrology example? No? There will also be time to ask questions in the end. So I will then share the screen again. All right. So that was the hydrology example. We figured that we would also like to highlight some of the features that we think are the key features of the ModelSkill library. And the first thing is that we think that it's quite easy to make these multi-model and multi-observations comparisons. And then also that you have all the metrics and the plots that you need, or at least the basic ones. You can, of course, also add your own plots, as Henrik just showed. You also have the possibility to add your own metrics. And you can, so you can go ahead and define your own metric and then add it in as well as you saw that Henrik added in some other metrics. Then we think that the filtering and the aggregations that are possible, for example, aggregating on a specific month or filtering on a specific area, or also doing aggregations or filtering based on auxiliary data that we will see a bit later today, is really powerful. And of course, all those things you can do with your own Python scripts. But since many people do similar things, we figured that it was really nice to put into ModelSkill to make it easy. Then we tried to make the API quite simple and also familiar if you know pandas and X-array. So many of the things that you know there are called the same things. For example, like in X-array, you have a SEL, select method, and we have the same here, also query. We have tried hard with the API to make the code readable so that you can use these chained up operations, as you also saw Henrik demonstrate. So we use this dot notation, so dot plot, dot KGE, etc., etc. The library is open and extendable, so you can do your own plots, add in your own derived data arrays if you want to during the processing. And it's easy to install and use. It's also documented and tested quite thoroughly. I think we have, I don't know, 500 unit tests running each time we make a change. And then it's open source and cross-platform. So as you already saw, Henrik just ran the ModelSkill library in a Linux container on the cloud in the Google Colab environment. And you can, of course, put it in your web server or whatever you want, or just run it on your local Windows PC. So yeah, so that was some of the features that we wanted to highlight. Let's now look a bit closer at the comparer, because that is the key object after you have compared or matched your data. So you can get a comparer either from the match method that I will show in a minute, or from the from match that Henrik showed. There are also, in parentheses here, a loads and a from config, because you can also, if you say you have hundreds of measurements, maybe you don't want to write them in by code, maybe you want to load them from a configuration file. We will not show that today, but if you can dig more into that in the documentation if you want to. So that can be from a YAML file or from an Excel file. After you have created your comparer or your comparer collections, you can also save it to an object and then load it again later. So, but a comparer has one observations and then one and more model results. Then it may also have some auxiliary data. You can access it, the data by the .data accessor. You can plot, as you saw with .plot and .something, like time series, scatter, QQ, KDE, and etc., and HIST. And then you have this table with the skill scores. That's also a key functionality here. And then the filtering can be done with the .set method and .query, and there's also a .where similar to Excel. If you have more observations, then you will also have more comparer objects, and these are conveniently put together in a comparer collections. You can do it like this, or you can also get it directly from the match method. You can then access a single of those again by just grabbing that component by the name, like this, with the get item method. And here you have the same API, more or less. You don't have the time series plot because it's less useful if you have multiple ones. So there you need to access the individual one to get the time series plots, but you can still do skill and filling in the same way. The library have actually been around for a while under a different name, but some of the new things that we have developed over the past year is making it easy to create comparisons directly from match data, then load save comparisons to file, and then also using auxiliary data and custom metadata. And then we have added the support for more data types and file types. We have also added the support for directional data. And then global settings and styling, and then much better documentation. Yes, so let's look at the second example now. So I'll just share a different screen here. All right. So this is a MedOcean use case where we have data in different files. So we have some observation data in different DFS0 files. Could also be CSV files and netcdf files. That's also supported. And then we have some model data which is stored partly in DFSU files. So those are the results from Mike 21, and then also from non-Mike models. I think we have some error 5 and one other. Let's get back to that, what that actually is. But they are stored in netcdf files. So we will first import ModelSkill as MS, as we always do. And then here I have also imported X-array, but that's actually only just to show you what kind of data that we're loading. But the task here is a little different than Henrik's, because here, since the data is stored in 2D files, we need to first extract spatially also. And there are different options there. I will not go through how you can, decide on the spatial interpolation and so on. That's a bit too much for this webinar, but you can see the details in the documentation. But let me first create 2 observations and also 1 track observation. So that's from satellite track altimetry. And then we will load first or create 2 model results. So you see that I'm calling model result here. I could also have called the class directly. It's called DFSU model result. And then I give it a name and specify an item. So here it's surface elevation data. No, it's actually wave data. Yep, sorry. That's it's a significant wave height. Sorry about that. So it can be useful to get this in a spatial overview. So you see here I have 2 stations. The outline of the flexible mesh model is also shown here, and then also the track data with color coded with intensity. So here you see that after defining these observations up here, point observation, track observations, and model results, I can then use the match method with multiple observations and multiple models. And then, let's take it one at a time. So I'll create first this compare collection. So since I give it multiple observations, it will already create a compare collection. I can then get a nice overview by assessing the skill like this. So here you see I have 2 different calibration runs, probably from the same model of Mike 21SW. And then you see the metrics as the same default metrics as before. Okay, but let's move to a third-party model result, because since I've now made these 2 different calibration ones, I would also like to see how does it compare against an error 5 wave model result. So before loading that into ModelSkill, I can just show you the data loaded with X-array. You see it as a number of different data variables here in the useful or maybe well known to some of you format of X-array. But I can also just directly load this file with the same command as above. So with .ModelSkill, ms.model_result, that was it. And then you see I refer the name of the item and give it a name so that I can easily recognize it. All right. And I can also just verify that it actually now contains the same data as above, except that I have selected a specific item here, or data variable, which is the SWH, the significant weight count. Yeah, also just to plot and see how that looks. All right, now I want to test how the extraction works from X-array. So I can also, you would not normally do this, but it's also, if you want to see it a bit more step by step, you can see here there is the model result also contains a .extract feature, which is implicitly called when you call .match. But then it will extract a specific position here into a point model result, and that can also be plotted like this. Yeah, I think I'll skip that one. Okay, it could also be that your model results, like in this CMEMS case, is stored in multiple files. So I can also give it a wildcard here. So similar as you would do with an open multi-file data set with X-array, you can do the same with ModelSkill. So you can see under this, and I can inspect the data afterwards. All right, let us get a temporal overview of this. because that's also possible with ModelSkill. So you see I say .plotting.temporal coverage, and then I get a nice temporal overview about for the coverage of the different models and the different observations. So the models are marked with bold here. Now, when I do the match, I will get the sort of the intersection of the different models here, so they are easy to compare. All right, so this method then goes into, for each of these different observations, then it goes into each of these data sets and extract in both space and time the model at the same times and positions as the observations. Okay, that was the matching phase. So so here we can also, of course, do some analysis and plotting. So I can do something like this, where I, for each of the observations, get a overview of the performance for each of the models. So maybe I could also select a specific observation here. So hopefully I'll get this right. No. So it's not like this. And then I can do the styling because there was no levels to swap after I have selected just a single observations. Yeah, but you see that the styling here adds, opinionated way of styling, so you can see which one is doing best and so on. We can also do a bar chart like this, which is then grouped on observations. And here we can also swap the levels if we want to see it grouped by model instead. It's also possible to do a mean skill, because maybe that's actually what you want to get at. So what is the mean performance across all the different observations? And as Henrik showed in the previous notebook, it's also possible to then add a weight here if you want to have different weighting on the different observations. Yeah, there's also a Taylor plot, but I think I'll skip that. And then let's go to some of the newer things here. One of the newer things, that is the support for directional data. So if you have wind direction, you have wave direction, or current direction, or something which can be relevant in a mid-ocean context, it's slightly different what you need to do. There are some metrics which are not valid, and also some plotting which are different and so on. So here we have a mid-ocean time series of some data, and here we use from matched because they're already matched in the same file. So there's a significant wave height, and then there's a mean wave direction. So let's first take just the mean wave direction, like this. You see that the quantity here is mean wave direction, the units are degree, and then is directional true. So that we set if we can automatically, but as it's also stated up here, you can also specify specifically that you want your quantity to be directional. And that is the key in order to get access to the circular matrix. So these are with it says C underscore bias, because the statistics is of course different in a circular situation. Plotting will also be slightly different in the way that we want to have ticks at the suitable positions and also stop it at 0 and 360. You can see you also get that from the KDE plot, but it's worthwhile noticing that the left and right endpoint here would not match, because we have that is not supported yet. The scatter plot is also slightly different because the QQ line doesn't make sense, and also the 1-1 line can be, or not the 1-1, but the regression line can be confusing here. So at least you get some sensible statistics and so on. There's also a possibility to do a rows plot. And you can actually do a dual rows plot. So if you have two data sets, here is the significant wave height as the magnitude, and then the mean wave direction as the direction for both model and measurement. You can do this wind rows plot, which can be useful if you're comparing directional data. All right. The last thing I want to show is pre-match with auxiliary data. Or matching with let's have a look here. So in this case, I want to do some aggregations which are based not on the data itself but on some other data. So in this case, I want to compare my significant wave height of the model and observation against each other, but conditional on say the wind speed or the wind direction. So I have added in here with the aux items arguments some auxiliary data that I want to have in my comparer, and then I'll just rename them because it's more convenient. And then you can see I have these auxiliary data. The comparer have of course, one observation, and then it has one model, and then these two auxiliary data, which you can also see here. So it doesn't really affect the skill plot, and I can also do the normal scatter plot and time series plot, no problem. But when I do the filtering or aggregations, I can then use that additional data that I have added in, and that can be really useful. So maybe I want to say, I only want the comparer when the wind speed is above a certain threshold. And I can do that both with the query and also with the where method. So now that I have this, I can plot only this. And as you see, we still keep the original model data, which can be useful for plotting, but the statistics and all that will be just on the filter data. I can also add in the residual. So that was also a remark that I had in one of the slides, that you have the possibility to add in your at any time your additional data for example, like derived quantities and so on. And here I'm creating a new column or a new data array in the data set, which is the residual. And maybe I want to look at the only when I have a large residual. So then I get these. Let's see, I can also aggregate. So the last thing I want to show, since I can see time is running here, is that I want to do a skill assessment based on wind sector. So this data set is very small, so I don't have north, west, east, and south, but just some of the sectors. So I've created some smaller sectors here. So I add in the wind sector. So just oops. Let's just see that, compare data. So here you can see there is now a wind sector. And now, since that is inside my object, I can filter based on that wind sector. So here you see the aggregated statistics based on the individual wind sectors. Yes. All right. I think that's enough for now. So just have a few more slides to share. The other screen. Yes, so that was the MedOcean test case. So already now version 1.0 of ModelSkill is released. So we consider this production ready and encourage you to start using it, build on top, build it into your own applications or web apps, etc. So with the mark of a 1.0 also that also shows that it's a stable release, so you can depend on the API. Of course, we cannot promise that it will never change, but it will not change a lot, and we will also be quite careful with deprecation warnings and so on if we change it from now on. We are still in the process of making additional training material and designing a course around this. And then, of course, we have a few leftovers that will soon be released in version 1.1. Like better colors and the mapping plots that Henrik also showed. And we also have more plans for this year in terms of working with forecast skill, probabilistic skill assessment, for example, from ensemble models, and also supporting more geometric types. And the very last thing is that, yes, there's a GitHub page for the code. We also have a documentation where we will soon add some more examples. And then we encourage you to contribute, get involved. If you have issues, if you have new ideas, then go to the discussion page on GitHub. And then if everyone is welcome to create a pull request with a new feature or a bug fix. So yeah, I think we already have like 10 contributors, but we are welcoming more. And also, if you want to support the future development, we will also be happy to if you give us a star on GitHub, because then it can actually be quite difficult to show how much these open source tools are used. So if you want to support ModelSkill and our continued development of that, you can maybe give us a star on GitHub. That's all. Thank you.